So we'd like to get work in some examples of diagonalizing matrices, but there's still a little more theory we need to get through. So far, in our very first video, we looked at a preliminary result. I called this theorem. If V1 through Vr are eigenvectors of A corresponding to distinct eigenvalues, lambda 1 through lambda r, then those eigenvectors form a linearly independent set. That's a really important result. And then in our second video, where we actually began defining diagonalization, we proved the diagonalization theorem that says A is diagonizable if and only if A has n linearly independent eigenvectors. That's an incredibly important result. We're going to put these two results together to come up with what's called a corollary. So a corollary is something that follows from other results. That's what a corollary is in mathematics. It's a result that follows from other results. So here's a really useful corollary. Sometimes this will speed things up just a bit. It says if A is an n by n matrix with n distinct eigenvalues, then A will be diagonizable. Is diagonizable. So that's really useful. So all you have to do to be able to figure out if something is diagonizable, this is one technique. It works in one direction. That is, if you can find, let's say you have a 2 by 2 matrix and you can show that it has two distinct eigenvalues with the characteristic polynomial, then you know it's diagonizable. But just because it's diagonizable doesn't mean it has n distinct eigenvalues. It's only a one way, right? Diagonizable does not mean it has n distinct eigenvalues, but n distinct eigenvalues means diagonizable. So that's useful some of the time. Let's go ahead and prove this. Really easy proof. I told you this is a corollary. It depends on previous results. It's a proof. So we're going to assume the part after the f, right? Suppose A is an n by n matrix with n distinct eigenvalues. So no repeated eigenvalues, no repeated multiplicities. Distinct eigenvalues. Lambda 1, lambda 2, through lambda n. So these are all distinct. No repeated eigenvalues. So lambda 1, lambda 2, through lambda n are all different. Let V1, V2, through VR be the associated eigenvectors. Okay? Now, what we're going to do, we're going to go back and we're going to use one of these previous results. What result can we use here? Well, if you have V1 through VR eigenvectors of A with corresponding distinct eigenvalues, lambda 1 through lambda r, then the set of vectors is linearly independent. So our V1 through Vn, that should have been an n there. I don't know why that's an r. By a previous result, that's the one above at the very top. By a previous result, the set of vectors V1 through Vn is linearly independent. So the question is, what can you use now if you have a set of linearly independent eigenvectors, right? These are eigenvectors. Well, now you can use the diagonalization theorem, right? Diagonalization theorem says if A has n linearly independent eigenvectors, that's what we have right here, right? We have v1 through vn, right? N linearly independent eigenvectors. That means A is diagonizable by the diagonalization theorem, by the diagonalization theorem. A is diagonizable. And that's what we wanted to arrive at, right? We were assuming A had n distinct eigenvalues, and we want to arrive at A is diagonizable. And that's what we've proven. All right, let's actually do a little work. Let's do a little work. We want to do an exercise here. Get one exercise in, at least. Diagonalize A, if possible. I'm going to start off with a 2 by 2 matrix. Remember when you're doing diagonalization, when you're doing eigenvectors, eigenvalues, we're always talking about square matrices. So we're going to start off with a 2 by 2, a smaller matrix. It's going to be 1, 2, 3, 2. We're going to figure out, can we diagonalize this or not? And if so, we want to diagonalize it. All right. So the first thing we're going to do, our kind of first step, we're going to find the eigenvalues. Find real eigenvalues. So we're going to look at the characteristic polynomial set equal to 0. So that's determinant of what? A minus lambda I2 equal to 0. So lambda is an eigenvalue of that if and only if that characteristic polynomial is satisfied by lambda. So let's see, that's going to be determinant of, I have what, 1 minus lambda, 2 minus lambda. So subtracting lambda off the main diagonal and then keeping the other values the same. It's equal to 0. Let's calculate that. This should all be in red here. So we're going to take the determinant. We're going to have 1 minus lambda times 2 minus lambda. That's the product of the descending diagonal minus the product of the ascending diagonal. 2 times 3 is 6. That's equal to 0. All right, we're going to scroll. We're going to FOIL. We're going to have what? 2 minus 3 lambda plus lambda squared. Then on the to the right of that minus 6. That's equal to 0. We're going to have what? Lambda squared minus 3 lambda. We're going to combine like terms here, right? We got some like terms. We have what? 2 here and minus 6 give us minus 4. All that's equal to 0. We can factor this into lambda minus 4, lambda plus 1. So we're going to have 2 roots to this equation. Lambda equals 4, lambda equals negative 1. So already we have what? 2 distinct eigenvalues. No repeated eigenvalues, right? No eigenvalues of like multiplicity 2. So we have 2 distinct eigenvalues. So that means this is diagonizable. We can already tell that. A is diagonizable since there are 2 distinct. Right, we're talking about a 2 by 2 matrix, so you'll want 2 distinct eigenvalues in this case. 2 distinct eigenvalues. Now it's possible you could get a eigenvalue, a single eigenvalue like lambda equals 4 of multiplicity 2, and it's still possible to diagonalize it, but you'd have to do more work to be able to tell. So we know it's diagonalizable. Now let's actually let's find the P matrix and the D matrix. The P matrix and the D matrix. So to do that, we're going to find bases for our eigenspaces, right? We're going to have 2 eigenspaces, 1 for each eigenvalue. We're going to have an eigenspace for 4 and an eigenspace for negative 1. So step 2, we're going to find bases for our eigenspaces. So step 2, find basis for each eigenspace. All right, so here I go. I'm going to find the basis for the eigenspace associated with the eigenvalue of 4. Okay. So I'm going to look at A minus lambda I, 4I, augmented with the 0 vector. What is that exactly? That is the matrix consisting of what? So matrix A is what? 1, 3, 2, 2, and we're going to subtract what? 4 down the main diagonal, and then we're going to augment it with zeros. So we're going to have the matrix what? Negative 3, 2 down the first column, and 3, negative 2 down the second column, and then 0, 0 down the far right. Can row reduce this, right? I can multiply the top row by 2 and the bottom row by 3, add those together. Things are going to cancel. We're going to get this row reduces to negative 3, 3, 0, 0, and then zeros on the right. So when I'm looking at a general solution of this, a general solution, where our second column is going to be a non-pivot column, so x2 is free. We need to find x1 in terms of x2. We got what? Negative 3x1 plus 3x2 equals 0. I think x1 is going to be x2 here. So x1 is equal to x2. Now let's look at the vector form of this solution. Vector form of solution. It's going to be the vector consisting of what? x2, x2, which you can factor out. x2 out front, and you're going to get 1, 1 as for the vector. So any vector of this form is an eigenvector for the eigenvalue 4, except you can't plug in 0 for x2, right? x2 can't be 0. x2 can't be 0. When you're talking about actual eigenvectors. So that means a basis for the eigenspace, so I'm going to write that in purple. Basis for the eigenspace of A associated with the eigenvalue of 4. That's going to be, I'm going to call it B is going to be 1, 1. Okay. So we need to do that again for the other eigenvalue. Where am I going to do that? I'm going to do that here to the left. Oh, what was my other eigenvalue? Negative 1, right? So I need to take A minus lambda, negative 1, times I, augmented with the 0 vector. Now that double negative is going to give us a plus. So I'm going to have what? A, what was matrix A? I forgot what matrix A was. It was 1, 2, 3, 2. 1, 2, 3, 2. No, let's give some more space because we're going to have to add 1. 0, 0. Okay, so the diagonal we're going to have 1, add 1. It's going to give us the matrix, what? 2, 2, 3, 3, and then zeros. So we're going to row reduce this as well. And when we row reduce this, we can multiply the top matrix by 1, the bottom matrix by negative 1, and you get what? 2, 3, 0, 0, 0, 0. And you want to find a general solution here to this associated linear system. So we're going to look at a general solution. So we're looking here, this guy, what is this guy called? The second column, it's a pivot column, a non-pivot column, so x2 is free. We got to find x1. Looks like we have the equation, what? 2x1 plus 3x2 equals 0. That means what? X1 is going to be what? Negative 3/2 x2. So when you're looking at your general solution in vector form, you're going to have what? The solution vector will look like 3/2 x2, x2. So you can factor out an x2, and you're going to have 3/2, 1. So as far as a basis, for eigenspace of A associated with, what was it? -1 was the eigenvalue. I'm going to call this script E is the basis here. It's not a script E, is it? Come on, right, please. Thank you. Script E is going to consist of single vector 3/2, 1. All right. So, in the diagonalization process, A, that was our matrix, equals P, D, P inverse, where P is going to consist of your eigenvectors from the bases. So we have what, 1, 1. That was your first, right? 1, 1. 1, 1. That was the basis for the first eigen space, and the second eigenspace you had 3, 2. 3/2 and 1. Now that's what your P is going to look like. And your D is just going to be a diagonal matrix with the eigenvalues in the order that you found them. So they were 4 and -1. 4 and -1, and then you put zeros everywhere else. So this is the diagonalization scheme right here. Your original matrix A is going to be equal to P, D, P inverse. Yeah, so you could say that basically here, that A diagonalizes to D, right? Diagonalizes to D. So these two matrices are similar via P,